Hello everyone, welcome to AOS-CX 10.11 update. So I am Shobna, Technical Marketing Engineer, Aruba Campus Switching. So in this session, we'll see about DoDin APL Certifications update. This is the second session. We have other sessions also available for this certification. It has been already posted. So in this session, we'll see about security in 8325, BGP Peer Authentication using TCP AO, IP tunnel, SNMP MIP support. As part of today's session, we'll see about the abbreviations involved in this session, overview about DoDin APL certification, and enhancements in 10.11 like security in 8325, BGP peer authentication using TCP AO, IP tunnel, SNMP MIP support. Let's start with the abbreviations. Following on the abbreviations will be used in this session: DOD, Department of Defense; DISA, Defense Information System Agency; APL, Approved Product List; AO, Authentication Option. Let's jump into the overview. So before we see the feature-specific overview, let's start with the overview about DoDin APL certification. The Defense Information System Agency maintains the Department of Defense Information Network approved product list process on behalf of Department of Defense. This process provides a single consolidated list of products that have met the cybersecurity and interoperation certification requirements. The DoDin APL is an acquisition decision support tool for DoD organizations interested in procuring equipment to add to their DISN network to support their mission. The US government and defense organizations will only procure products that compile with DoDin APL process for the Department of Defense networks. So far, we have seen about DoDin APL certification. Let's understand the new enhancements added in 10.11 for upgrading this certification. The AOS-CX switches operate under strict adherence to international and US government computer security standards in order to meet or exceed the demands and requirements of national agencies, organizations, and other publicly funded institutions. Most of our switches are DoDin APL certified from 10.6 release. Once a product is certified, the DoD components perform upgrades and maintenance for the life of the product to meet ongoing security requirements. Hence, these enhancements are updated to the existing certification. These enhancements is mainly a host of tertiary security features required to ensure more security in our switches. So the enhancements are in 10.11 like security in 8325, BGP peer authentication using TCP AO, IP tunnel, SNMP MIP support. So in the coming slides, we'll see more details about these enhancements. Let's see about security in 8325. Before that, let's see a quick recap of our Aruba-CX switching portfolio. Our switching portfolio spans from access to the core layer. We have pure access switches 6000 and 6100. And there comes our 6200 and 6300, 6400 boxes that moves from access to the aggregation to the core layer. And comes our data center switches Aruba-CX 83 series like our 8325, CX 10,000, CX 8400 and CX 9300 switches that span in the data center, that is the core layer. And we have our ruggedized Aruba-CX 4100i acting in the access layer. So today our hero is Aruba-CX 8325, that is present in the aggregation to core layer. So built from the ground with a combination of cutting-edge hardware and software, our Aruba-CX switches are designed for today's enterprise campus, branch, and data center networks. Here are the use cases of how they are being used in small and large campuses and where they can reside. So when we see our Aruba-CX 8325, in the small campuses, it can act as a core switch, like a collapsed core layer. It can act as either in standalone or in a VSX combination. When it comes to large campuses, they can reside in the access aggregation layer or even in the standalone core layer. So far, we have seen how our CX 8325 switches are placed in our switching portfolio. Now let's see what is the enhancement added in this 8325. As part of this DoDin APL certifications, our 8325 switches are more secure enabled, like we have our port access and network defense features supported in our 8325. Let's see the use case of how it can be deployed. So we all know in the access layer, we can have endpoints connected, and these access switches are already enabled with port access and network defense security features. So with the addition of security in our aggregation layer, like our 8325 when placed in our aggregation layer or in core layer, so they make sure only an authenticated access switches can connect to this aggregation or core layer. So we are adding additional capability of security in aggregation and core layer apart from the security we add in the access layer. The end clients, once they are connected to the access switches, they will get authenticated by the access switches. So once they are authenticated by access switcher, the traffic will pass from the access switches to the aggregation core switches. So we have multiple access switches connected to the core switch. So we can make sure only the authenticated access switches can connect to the aggregation and core switch. So that can be possible only if security is enabled in the access or aggregation layers. So with the support of security in 8325, that is possible now. So let's see what are the security features and network defense features that are supported in 8325. So this is a matrix that represents the list of features that will be supported in 8325 and which are planned in CP release 10.11.1000, which will be not supported in 8325 currently, and which are the security features that are already available. So if you see here, the list of features supported in 10.11 release is 801x with TLS authentication, MAC auth, and auth precedence, auth priority, concurrent onboarding, all the secure role features, and radius port access like accounting tracking, COA, radius server tracking, MAC lockdown, MAC based VLAN, cache reauth, post reauth, log offlines, max VLAN support, violation infra, port security, sticky MAC, and it will have the scale values parity with our existing access switches 6300. SNMP auth clients map, port access web UI, device profile with MAC match, RADSEC user authentication. RADSEC management authentication is already present. DHCP v4 snooping, IPv4 lockdown, snooping and relay coexistence. And these features will be supported in the CP release like MDA, VLAN pool, mixed role, RADSEC, port access security. And then CREAF and support for .NET supplicant and ARP security. And these are list of features that will not be supported currently for this 8325. And 8325 add minimum other management authentication features already available in it during its initial deployment as well. So like local user management, radius, TechAC, SCPA, SFTP, PKI, DHCP server day, SSH server and client, job scheduling, and RA guard. So in the demo, I'll be using the same topology. I will have an endpoint connected to the access switch. Access switch, I have taken CX 6400 box, and from the access switch, it will be connected to the CX 8325, that is our code layer box. And then from there, we will have our clear class policy manager connected as a radius server. So I've opened the three tabs. The first one is for the 8325 box. The other one is for the 6400 box. The other one is the end client. So currently I'm trying to ping the core switch, that is the 8325 box from the end client. So it is pinging in background. Now there is no security enabled in any of the switches. So now let's enable security on the switch. First in 8325. I'll try to enable security on the port connected to the 6400. Let's see what happens to the end client now. We'll try to configure first the radius server. Next is we'll try to enable .NET and MAC authentication globally. Now in the port connected to The port connected to the 6400 box, the access layer, will try to enable security. I will try to enable concurrent onboarding. So if you see here, this MAC authentication has been failed state. So now the ping will be dropping. Yeah, since we have enabled security, so any traffic that is coming to this switch will be dropped. Now, we are not only securing the endpoints, we have to secure even the access switches that are getting connected to the code switch. So for that purpose, what I will do is first, I will try to authenticate these endpoints in the access switch, and then the access switch will be authenticated by the core switch. So I will try to enable .1x supplicant in the access switches, and the core switch, the 8025 will act as a .1x authenticator. So first we'll try to onboard the end clients in this box. So we'll enable .1x and MAC authentication in the access switch globally. So these are the relays we enable the .1x and MAC authentication globally. And I will try to use the radius server config. Next is I will try to enable the incline connected port, .1x and MAC authentication. Before that, I will create a role for the incline. Just provide a VLAN. And then the interface connected to the incline. We'll see for the MAC address table. It is connected to 14. Here I will try to enable .1x and MAC authentication globally with concurrent onboarding. So now let's see the configuration. So .NICE and MAC authentication is enabled globally with concurrent onboarding. We'll see whether the client has onboarded. It is in progress state. We'll see why is it in progress state. Because it is server timeout. We have enabled security between the core switch and then the access switch. So all the radius packets that is originating from this access switch will not be able to reach the core switch, and from there it cannot reach the server form. Hence, we have to make sure we enable security between the core switch and the access switch. So I'll try to make this switch as a .1x supplicant. So I'll try to enable .1x supplicant here. So globally, we have to go to the .1x supplicant context and we need to create a policy. So here I'll try to configure a EP identity. And password same. And EP method, I'll keep it as MD5 for now. We'll try to enable the DoDin applicant globally. In this applicant context, I'm enabling it. And I will try to enable the DoDin applicant and the port connected to the authenticator. But before that, we need to create roles in the authenticator. So I'll create a role for the switch, access switch. I'll place it in the same VLAN. And the auth mode should be device mode. So only then the clients behind the access switch, the end client can gain access and they can reach the core switch. So now I'll go to the switch and try to enable DoDin applicant on the port connected to the core switch. So the port connected to the core switch is let me check here. It is 1113 here. The other side is 1/3/13. So just enabled with the access VLAN. Now I'll try to enable DoDin applicant in it. So we need to associate the policy created before and then enable it. Let's see in the core switch now. So it still has this MAC address. We'll stop the traffic and shut the port and shut it. Since we have given only one as the client limit, only one client can onboard here. Shut, no shut. So now the access switch is onboarded. We'll see whether the access switch clients can onboard now. Yes, even the end client has now onboarded and provided with the end client role. Now we will try to ping from the end client. So now the ping is successful. From the end client, now we are able to ping the core switch. So the correct way to do is we have to enable security on the core switch and make sure only authenticated access switches can connect to the core switch, and even we have to make sure the authenticated clients only can connect to the access switch. So it is a full way security from the access layer to the core layer. And it satisfies the major goal of Aruba, zero trust approach. Let's see about BGP Peer Authentication using TCP AO. This is also one of the features added in 10.11 for DoDin APL certification. BGP authentication enables the routers to share information only if they can verify that they are talking to a trusted source based on the password. So till 10.10 release, we had support for only TCP MD5 mechanism to protect the BGP sessions. But the TCP MD5 mechanism has more disadvantages. Let's see one by one. So it provides better protection, but has known weakness and vulnerable against collision attacks. The MD5 does not provide a mechanism to change a shared key for a connection, hence exposed to brute force attacks. Even though the MD5 is widely deployed till now, from security standpoint, it is deprecated owing to many security concerns. Hence, as part of DoDin APL certification, there comes a requirement to support TCP AO as authentication mechanism for securing our BGP sessions. Let's see about BGP peer authentication using TCP AO. TCP AO is the proposed replacement of TCP MD5 defined in RFC 2385. It is based on RFC 5925 and 5926. TCP AO is resistant to collision attacks and provides algorithmic agility and support for key management. TCP AO has the following distinct features. TCP AO supports use of stronger message authenticated codes to enhance the security of long-lived TCP connections. It protects against replays for long-lived TCP connection and coordinates key changes between endpoints by providing a more explicit key management. It allows for static or dynamic master key tuples across repeated instances of a connection and thereby uses traffic keys derived from this MKT and coordinates the MKT changes between endpoints. The TCP AO as per RFC 5926 specifies that two below max are must to be implemented like HMAC SHA-196, AES-128, CMAC 96. Let's see the use cases of BGP TCP AO. Most of the third-party vendors supports BGP TCP AO. So it becomes responsibility of our AOS-CX switches also to support BGP TCP AO, and it will be greatly helpful in environments where there is mix of third-party switches. As we discussed already, MD5 is having weakness and it is very vulnerable to brute force attacks. So MD5 is no longer be trusted one. Hence, there is a need for supporting BGP authentication using BGP TCP AO. So let's see some behavioral differences with TCP AO. So TCP AO and TCP MD5 features are mutually exclusive. So we can use only one of them. We cannot use both of them. So if a peer group is identified for TCP AO, then a peer in that group cannot be used for TCP MD5. So it should have all the peers in the group supporting TCP AO. TCP AO is not supported for dynamic BGP peers. The seamless key rollover feature will be supported only in subsequent releases. Let's see the configuration overview about the BGP TCP AO feature. We had our existing keychain feature that is enhanced for supporting this TCP AO. This keychain feature was used for other applications as well. Following are the new fields that are added at the keychain feature. So there will be an option to configure the send ID and receive ID. These values take a value in the range of 0 to 255 and must be unique across the keychain. And we already talked about two algorithms that is a must for this BGP TCP AO. So one is AES-128 CMAC 96, another was HMAC SHA-1. HMAC SHA-1 was already present in keychain, only AES-128 CMAC 96 option was newly added in this keychain feature. Now let's see what are the new configurations that has been supported in this BGP. So in the BGP peer level, we have config to specify the keychain which we created already. And we will have an option to configure the TCP AO connection, whether it should include the TCP header options while calculating the MAC, and whether the peer should accept the TCP connection even if the peer does not support TCP AO option. So these are the new configurations that will be supported in BGP TCP AO. Let's jump into the configurations. First comes the keychain configurations. So these are the configurations that are available in the switches already. So the black highlighted ones are the new ones added as part of BGP TCP AO. So first comes the keychain. Then we have to go to the key and specify the key ID. Inside the key ID, we will have option to configure the cryptographic algorithm to be used for BGP TCP AO. And then we will have the receive ID and send ID. It will mention this receive ID corresponding for the key instance and then send ID corresponding for the key instance. And apart from that, for the keychain, we need to have the other configurations like key name and then the key string. And optionally, we can mention the send lifetime and accept lifetime. Those are the pre-existing CLA options already available in keychain. So once we have configured this keychain, there comes the option to associate that keychain for the BGP peer. So we have to go to the router BGP context, and for the particular neighbor, like this is peer specific configuration. So we need to mention neighbor and then the neighbor ID and mention like authentication option TCP. And once we mention the TCP AO as authenticate option, we have to associate the key by specifying the key name And we have other additional options like accept AO mismatch, like accept the incoming TCP connection with no matching MKT. And there's other option like include TCP options. This will have the inclusion, the TCP header options for the MAC calculation. Let's see what are the show commands that has been enhanced for this feature. First comes the show keychain. So this is also a legacy show command, but it will have options to display the BGP TCP AO options like send ID, receive ID, and then the crypto algorithm that has been used. And next comes the show BGP unicast neighbors. So here it will display the TCP AO keychain associated for the BGP peer, and what is the current key, what is the send ID, what is the receive ID, and whether include TCP option is enabled, and whether accept AO mismatch is enabled or disabled. So this is also the existing show BGP commands, but the show command options has been enhanced to support the TCP AO options. Next comes the best practices. So these are the practices we need to follow for this BGP TCP AO. The key string, the send lifetime, and the cryptographic algorithm of keys must match on the both the peers. So if we have different keys or different algorithms, then the BGP TCP authentication will fail. The key send ID of one peer should match the receive ID of the same key on the other peer. And it is recommended to use the same ID value for both the send ID and then the receive ID. Before modifying any properties in our keychain other than send lifetime, it is advisable to dissociate the key from the BGP session and then do the modifications. Let's see the parity analysis. First comes our AOS switches, that is our ProCup switches. So those does not support the BGP TCP authentication. They support only MD5 password. Next is our combat H3C switches. They support BGP TCP AO, but they have support for only the HMAC algorithm. There is no support for AES algorithm. So the configuration is also same, like with the peer, we have to create a keychain and then associate the keychain with the peer. Next comes the Cisco. Cisco is exact replica of how our AOS-CX switches supports. It fully supports the BGP TCP AO, and here also the CLA configuration is per neighbor. We have to create a keychain and associate that keychain to the neighbor. And it are same options like include TCP and accept AO mismatch connections. Let's see the troubleshooting part. First, if the BGP session is not established, what type of troubleshooting we will see. So we have to identify whether the peer has TCP AO configured or not. And if it is configured, whether the key is valid between the peers. And if there is any mismatch of include TCP options config for the BGP peers. For this, we can have this debug BGP all enabled. It will display all the TCP AO debug messages. And even we can open the kernel D message and then identify the reason, like it will mention like TCP authentication failed, or authentication unexpected with the reason as rejected, authentication unexpected with accepted, or authentication missing with rejected, or authentication missing with accepted. We can also check the output of this file like proc.net tcp underscore auth opt. So it will display the send ID, receive ID, then the address. So those the information to be displayed in this file. And also we can capture the TCP dump output of for any mismatching keys in the TCP packets. Next, when we are seeing issues like TCP session is getting reset, like BGP establishment is getting reset. So it can happen because of rollover of keys, or the valid keys are expired, or subsequent mismatch of the keys. So same as above, we have to use this debug BGP all to identify the key expiry or rollover of keys. And additionally, we can check the send ID and receive ID whether they're configured correctly. Let's jump into the demo of BGP TCP AO. For this demo, I'll be using two 8320 switches and they are connected. Let me open the console of the switches. So they are in factory default configuration currently. So we will try to configuration. So we'll name it as peer A and peer B. So they are in 10.11 version. As a prerequisite, we'll try to configure the keychain first. I'll go to the keychain and name the keychain as KC1. So inside the keychain, we need to create a key. I'll create a key as 1. So inside key, we have first the cryptographic algorithm. The following two algorithms supports BGP TCP AO, AES-CMAC 128 and HMAC SHA-1. I am planning to use AES-CMAC 128. The same algorithm has to be enabled both the sides. And then I'll create a key name as 1 as well. And the key string, even here this key string has to match plain text TCP AO1. And then I'll configure send ID as 10, receive ID as 11. So in the other peer B, we have to configure the reverse way like send ID as 11 and receive ID as 10. And then I'll configure the accept and send lifetime as duration 6000 seconds, send lifetime duration 6000 seconds. So we'll see the configuration. So it will display the keychain. Key is created with key name, send ID, receive ID, key string, cryptographic algorithm, and accept lifetime and send lifetime. So once we have enabled it, I'll try to do the same configuration in the other peer. Keychain, KC1, key 1, and the key name 1, key string, plain text, and then the cryptographic algorithm AES, send ID, and like I said, it's a reverse 11, receive ID as 10, accept lifetime duration as 6000 seconds, send lifetime duration as 6000 seconds. So we have configured all the required CLIs for the keychain. Next, we'll try to establish a connection between these switches. So I'll try to enable IP address. Similarly in peer B. Next, I'll go to the peer A and try to configure the router BGP. So here comes a neighbor configuration. So this TCP AO is specific to the neighbor. So the particular neighbor, we have to configure the TCP AO option. First, let me configure the remote AES and the neighbor. I'll try to configure the TCP AO option where we can associate the keychain. I have created a keychain as KC1. I will associate here. We'll see about the other TCP AO options like accept AO mismatch and include TCP options later. In address family, IPv4 unicast. We'll activate the neighbor. When we enable router BGP, let's see what is the status of BGP. So currently it is only in connect state because the other side we have not yet configured the router BGP. We'll check whether the peer is pinging first. It's pinging. We'll go to the other peer B. We'll try to configure the same router BGP. We'll try to enable TCP AO with keychain name KC1. and we'll activate the neighbor. We'll enable router BGP. So now let's see the other side whether it got established. So now it has established and messages also are received and sent. We'll see the other show command. Show BGP IP for unicast neighbors. So this will also display the keychain, current key, the cryptographic algorithm used, send ID, receive ID, and number of messages sent and received. So let's try to capture the packet and see the packet level, whether the TCP packets are sent or not. I will go to the default BRF, try to capture the port connected to the other peer. It's port 1 with verbose mode, and I will capture only TCP packets. We'll wait for the package to come. We'll see the other side. So now there are 4 messages sent and received, and it's also an established state. We'll wait for the other message to be sent and received. So 5 messages sent. So if you see here the messages, so I will stop the message transaction here. So when you see here, this is the packet. So it is sent from 112 to 111. So it contains the TCP options, TCP AO as a keep alive mechanism. And then it mentions the key ID. What is the receive key ID? And what is the calculated MAC? So all these details will be available only if we have TCP AO options enabled. So this way we can validate like packet exchange happens only via the TCP AO. So now this MAC is calculated without this TCP options. So if we wanted to calculate this MAC based on the TCP options, we need to enable the include TCP options. So we'll go to the router BGP context. So here with the AO option, so we have this include TCP options. So this, when you enable this option, the MAC calculation will happen along with the TCP options, but it has to be enabled on the both the sides. Only then the MAC calculation will be correct and it will be accepted by the other peer. So let me include only in this peer. So all the sessions will be reset. We'll see what happens now. Because the other side, we have not yet established the TCP AO with the include TCP options. So it went to the connect state. From establish, it went to the connect state because the other side, the include TCP option is not enabled. Let me include that option in the other peer as well. So here also it will move to active state because it was not able to establish the BGP TCP AO with the peer A. So I'll go to the router BGP context, neighbor. Will enable the include TCP option, and we'll see now. So now it had moved to the established state. So it is mandatory to configure this include TCP options in both the side. It cannot be included only in one side. If it is enabled on only one side, the connection will not be getting established. So now the connection is established. Let's see the other option. So other option is accept AO mismatch. So why this configuration is required is like if some of the other peers does not have this TCP AO enabled, we wanted to decide whether we are planning to accept those BGP connections or not. So for that, we have given this optional AO mismatch command. So this is a security violation, but for other use cases like having a peer with not security enabled, this option is given. So when we enable these options, if the peer is not sending the TCP AO option, even then we'll accept the BGP connections. So let's enable here. So I have enabled only one side. So now it will be in established state only because the other side is also enabled with TCP AO. So let me disable the TCP AO on other side and I will check it out. So I have unconfigured it. So let's see now here, it moved to active state. Now it has moved to established state. We'll see whether it accepts the connections. We'll try to capture the packet. So we'll wait for the packets to come. So the packet has happened. The TCP AO connections are accepted. So now we have come to end of the demo. Hope everyone understood the BGP TCP AO authentication workflow. Let's jump into the next feature. Next comes the SNMP MIP support for the IP tunnel. The IP tunnel is available in our AOS-CX switches, but previously we didn't have any support for the SNMP MIPS. So as part of DoDin APL Certification 10.11, we will have support for the SNMP MIPS. So this SNMP MIP for the tunnel is supported via RFC 4087. And this SNMP is only a read-only access for the MIPS, and it is supported for the following tunnels: L3GRE tunnel, IPv6 and IPv4 tunnel, IPv6 and IPv6 tunnel. So this is a tunnel MIP and it contains the following tables: tunnel IF table, tunnel config table, tunnel INET config table. The tunnel IF table contains information about the tunnel like local address, remote address, encapsulation method, hop limit, security, TOS, flow label, address type, local INET address, remote INET address, and then the encapsulation limit. Next comes the tunnel config table and tunnel INET config table. So both these tables are also containing the tunnel information, but they're also used for mapping the tunnel endpoint to the if index. So they will contain the tunnel config if index, tunnel config status, tunnel config if index, config status, and config storage type. So let's check the SNMP walk output for this tunnel MIP in the coming slides. Let's see the sample SNMP walk output of the tunnel MIP. So this SNMP walk output is captured with 3 tunnels. 2 are IPv4 and third one is IPv6. Let's see the explanation of each of the tunnel MIP objects. First comes the local address. This is the source address of the tunnel endpoint. These are the IPv4 address. Next comes the remote address. This is the remote address or the destination address of the tunnel endpoint. So these are the IPv4 address. So this MIB object will only display the IPv4 address. For IPv6 address, it will display as all 0. So if you wanted to view the IPv6 address, we should use this INET address MIB objects. Next comes the encapsulation method. This represents the encapsulation method used in the tunnels. We have one tunnel with GRE, other tunnel with XARX, that are 6 in 4 or 6 in 6 tunnels. Next comes the hop limit. It defines the IPv4 time to live or the IPv6 hot limit to use in the IP header. So currently it's been configured with 64. Next is the security MIB object. So it will represent if there is any security enabled for the IP tunnel. Since we don't support security, it is mentioned as none. Next comes the toss. The tunnel is used to set the high bits, the differentiated service code point of the IPv4 type of service or the IPv6 traffic class in the outer IP header. So the value of -1 indicates that the bits are copied from the payload's header. Next comes the flow label. It is used to view the IPv6 flow label value. This object is supported for tunnels over IPv6. The default value of this object is 0. Next comes the address type. It shows the type of address in the corresponding tunnel endpoints. So we have two tunnels with IPv4. The third tunnel is IPv6. So it displays IPv4 and IPv6. Next comes the tunnel IF local INET address. This is the source address of the tunnel endpoint. And next comes the remote INET address. This is the remote or the destination address of the tunnel endpoint. So here the address format is represented in the INET address. So we are able to see the IPv6 address as well. Next is the other MIB objects. Next comes the encapsulation limit. It shows the maximum number of additional encapsulations permitted for packets undergoing encapsulation at this tunnel endpoint. Next comes the tunnel config if index. This shows the value of if index corresponding to the tunnel interface. So we have 3 tunnels. It associates the if index for these tunnels. Next shows the config status. This shows the status of the tunnel endpoints. For all the 3 tunnels, it shows currently as active since the tunnels are active. Next comes the INET config if index. This is similar to the config if index, where it shows the tunnel information in INET address format and the associated if index. And similarly, the config status shown in the INET address format with the config status of the tunnels. Next comes the config storage type. So this indicates the storage type. Only a non-volatile storage value is currently supported for the tunnel endpoints. So now we have seen the detail about the SNMP walk output of IP tunnel MIB. Thanks everyone for watching this recording. If you have any further queries, do post your queries in our adherence community.